So now in this lecture, I'm going to introduce you to something known as gradient descent for linear regression. And essentially, we are going to, well, let me just get back to my starting position. And essentially, I'm going to introduce you to the idea of carrying out linear regression from the first principles. And that is important because in doing so, I'm going to introduce you to some terms and that we are going to encounter a fair bit throughout this course. So as you know, and as we discovered before, regression is useful when we want to explore the relationship between numerical input features and the target values, and the target values are usually the predictor variables, and the input features are usually the predictors, and the target values are the response variables. And essentially with this we can get the continuous value output for unknown data. And suppose we have data set of house price and size of the house, and what regression can do is actually help establish a relationship between the size of the house, which is my predictor, and the response variable y. So how exactly does size of the house influence the price? And that's something we can ascertain using ordinary least squares regression, and we have already covered that previously. And this is what linear regression looks like. Y, which is the dependent variable or the outcome variable or the response variable, and the x's are the independent variables. We also call them predictor or explanatory variables, and essentially we can model the relationship between the independent variables, something like the size of the house, and the dependent variable, the price, because price depends on the size. So in linear regression, the relationships are modeled using linear predictor functions whose model parameters are estimated from the data. So if we have a scatter plot with some points on it, the object is to draw a line through these points so that they're as close as possible to the points, and essentially minimize the error. So this line, this is the point. So while this point lies on the line, this point doesn't, and the whole point of ordinary least squares regression is to minimize this error, because obviously a straight line won't go through every point. So in simple linear regression, we have one independent variable, and that is used to predict the value of one dependent variable. And as you can see, this is the estimated line, and the difference between the value over here and the actual y value is the error, and we want to minimize that. So essentially this is how we fit the line as we've seen before. And the easiest way of solving is by introducing a constant term MO with bias, and its value is 1, and then we are going to, and basically this helps us develop a cost function of linear regression, which helps establish the relationship between y and x. So the this equation called hypothesis x function is used to map input to output, and that's how the cost function comes into the picture. And as discussed above, and cost function is something we are going to encounter a fair bit throughout this course. So the linear regression algorithm, it finds a relationship between the input features, the x's, and the output features, and we want to fit the line to a data set such that the prediction error is as small as possible. But the question is, how do we measure this error to find out if the algorithm is giving the right predictions or not? And the answer is cost function. And using cost function, which is also known as loss function, we can decide whether the parameters of our algorithms are good enough to make accurate predictions. And the two kinds of linear regression cost functions or loss functions, and I'm going to use this term interchangeably. Our mean absolute error or mean square error, and mean square error or L2 is by far more common, and it measures the cost by taking the average square difference between the actual output and the predicted output, and the cost is a single value which represents the current set of weights or parameters, and the idea is to make this cost or the mean square error as small as possible. And so linear regression cost function. So given our hypothesis, well, this is the line of the linear regression. So this is how we get the cost function, where n is the examples in data sets, y is the actual label, and this is the predicted outcome, and we just subtract them, and we want to minimize the cost function. So less value of cost function, the more accuracy we get. And essentially, so we check the model cost. So this is the m value, the b value, the x and y, and these two predictors, they help us, these two values, they help us develop the relationship between y and x. And this is how the cost function, I'm not going to go into the mathematics of this because this is something you can understand. And from we can say M1, the algorithm is minimum at 51. So M1 is equal to 1 is the most appropriate weight for our linear regression algorithm because error at this weight is the lowest. So this is something we try to identify iteratively like so. And where we get the lowest value of the cost, that is the variable value, M1 value we go in for. So our goal will be to choose weights in such a way that our cost function is minimum. So minimum cost M1, and the idea is now how do we optimize our weights in order to minimize our cost function, and for that we implement something known as the gradient descent algorithm, and with this we can optimize weights, and I'm going to cover this very briefly. So this is the equation of linear regression. These are the parameters I have. This is my cost function, the difference between the predicted y and the actual y, and I want to minimize these values in a way to get the lowest cost function. And we are going to implement the gradient descent algorithm to find the best set of parameters to minimize the cost, and it optimizes. So this algorithm optimizes the parameters to minimize the cost function. It works in an iterative manner, and the idea is to move in the direction of the steepest descent by taking negatives of the gradients of cost function. So essentially this is our cost function in a two-dimensional graph. We want to find the minimum cost. So we start at the top left corner and we take step in the negative gradient direction, and we have to save our new position, recalculate the negative gradient to move further downhill, and we repeat the process till we reach the minimum point or the local minimum, which is the lowest cost function. And this is the mathematical equation for it. And to calculate gradient descent, we calculate partial derivatives with respect to parameters and weight, and alpha is learning rate, and learning rate is something that we are going to encounter further on, and essentially just learning rate helps us decide the kind of step function we take. And it is also very important to do simultaneous updates of the loop, and I'm not going to talk about implementing this gradient descent algorithm, but learning rate, we perform gradient descent in steps and size in steps. So, we move step by step, recalculate everything till we reach the local minimum. And the size of these steps is called the learning rate alpha. And with a big step size, our gradient descent will converge more quickly, but we could overshoot the lowest point. And with a small step, I think with a smaller step, we can be more confident about finding the minimum point, but then there's a cost of convergence. So yes, typically we keep the alpha value or the learning rate value pretty low in order to move step by step. So Again, we are trying to minimize this. So this is our gradient descent algorithm with partial derivatives. And after each update, finding the new parameters, we'll update them, find a new cost function, and just continue according to our learning rate. And this is the gradient descent algorithm. And these are the partial derivatives we take. And we are going to repeat this till we converge at the local minimum. And for linear regression, the key is the derivative term. And the derivative of cost function is shown here. I'm not going to talk through this mathematics. But essentially, we use the power rule and chain rule to carry out the necessary computations. And within Python, we have plenty of packages to do that for us. And basically, the cost of linear regression is a bowl known as a convex function. And this is ultimately how we get the cost of the linear function, like so. And optimization is where it can be observed how gradient descent updates its parameter values and reaches the lowest value of loss. So this is H0x, the current hypothesis, the current value, and the size x and the prices. And iteratively, it is moving in a way to try and fit all the points. And this is, and simultaneously, this is getting updated, these parameters. So ultimately, this is how, depending on our learning rate, the gradient descent will be computed with the view of minimizing the cost of the parameters, which ultimately will help us derive a relationship between y and x. And with this, I'm not going to go any further, but then these are some of the concepts, things like learning rate, gradient descent, and typically in Python or Pytorch, we end up implementing the stochastic gradient descent algorithm. So these are the things that we are going to encounter a fair bit throughout this course, and I am going to revisit these concepts more practically later on.